And so they measure what they can see the half-life is. So the half-life is a measure of after how much time is basically half of it gone. So they measure, they take a rock, they take a sample, and they say, okay, it's got, let's say 5%. And so normally, let's just say, and these numbers are totally bogus because they're really minuscule, but I'm just using bigger numbers to make it easier for the math. So let's say it's at 5%, and we know that normally it starts out at like 10%, okay? So if normally it starts out at 10, we're down to 5, then we know that there's been approximately 1 half-life because we're now at half. So the time of how old this rock is whatever that decay period is. And let's say, as we measure it now, it's 1,000 years, okay? So now we're down to this rock must be 1,000 years old. Well, the half-lives are, typically quite longer than that for some of these isotopes, and the amount decays quite a bit. So that's where they extrapolate back and say, wow, this rock must be 1,000,000 years old or 50 billion years old, and that's how they do it. Well, the problem with that is that there's a lot of assumptions. The main assumption with that is, one, is that the decay rates have been consistent over time, right? We have no way of knowing that. That's a pretty big assumption, because if you've studied, mathematical decays and stuff like that, a lot of times you see a very common pattern in mathematics and in physics is kind of an exponential curve, right? And once you get out onto an exponential curve, it looks pretty much steady state. So let's say that we're right here, so you have an exponential curve, let's say, that goes like this, or perhaps it went like this. And it's measuring decay rate, and so we're down over here, and we've been measuring the decay rate for the last 10, 20, 30, 50 years, and it's pretty consistent. But if we would have measured it right out here, it's like, whoa, the numbers are just totally different. And that decay rate could have been way bigger. So there's an assumption in there that we don't right now have a way to measure or to prove it, but that's something that is fundamental about most of the dating techniques that could totally throw a wrench into them. And also, and it's not uncommon for things to change in kind of an exponential curve like that. We see it a lot of things like the decay rates of sound and things. They kind of go as an x squared, which is kind of like an exponential. It's one of those curves, that kind of levels out over time. So things. So that's one of the things that, they say, well, we know because we date it with carbon dating and it's 50 billion years old. It's like, well, maybe, right? So, could be, maybe it is, maybe it's not. So and again, I'm just giving a surface level. There's a number of other issues that are involved. So for instance, I gave the example of a volcanically formed rock, just to show you about how things can be known to be wrong, is that a volcano happened in Hawaii, and they took and tested some of that rock, and they said, whoa, this rock is 50 billion years old. Like, wait a second, that just erupted. So something got off in their measurement there. That was just formed. So that kind of thing. Also, there's been datings, there's sedimentary layers. And sometimes something that we know is way up in a recent sedimentary layer can be dated back millions and billions of years. In fact, sometimes it's dated back older than stuff that's further down in the sedimentary layer. So it's like, Okay, so these dating things that they're using as hard and fast rules aren't always that accurate. In fact, there's a lot of fundamental questions, but right now they have no other way to do it, so that's kind of what they have to go with. But there's some fundamental problems with those dating mechanisms. So, now, Darwin's tree of life. Okay? Probably have seen it before, and again, it's that idea of that over time, everything started from a common ancestor. And there were mutations and things, so that over time you started with some very simple things and kind of branched out to be very complex. And so, if Darwin's theory was correct, if you would go back and look at the fossil record, is what you would see is way back when you'd have some very basic single cell organisms, and then you would have, you know, some more complex stuff, and then over time it keeps on building in gradual increments, so that if you would look at the fossil record, it would kind of go like this and would start growing in complexity over time. So the problem is that the fossil record doesn't go like that at all. Okay, well, Emmy's up there. There is what's called the Cambrian explosion in the fossil record. That's because, you know, they've named these eras, and one of the eras is called the Cambrian era. And what happened was that in that short little time, suddenly every major phyla that currently exists, boom, came into being. And before that, here's kind of what the chart looks like. It goes, and it's flat for all these billions of years, and then suddenly, wham! It's got everything. All of them. And I gave the example of, if you look at this on a, think of it in a measurement. So if you took a football field, if all of measured back history of the ancient rocks and the oldest that they think the earth is, let's say that whole span of time is 100 yards, like a football field. Well, you would think that over time, you know, there would be this gradual increase if the Darwinian theories were correct. Well, in fact, it doesn't. It stays like you have just single cell organisms all the way up until about the final 15th yard, which is then the Cambrian era. And in the space of one step, just less than a yard, boom, it's all there. Every single phyla that exists. So that totally is at odds with this idea of natural selection over time. Because now you don't have all of these billions of years for things to slowly change and develop. It just suddenly is all of there. And that's a huge, huge problem for Darwinists. They have no answer for that. And in fact, that they knew that was a problem back at the time of Darwin. But his assumption was, well, you know, we haven't found very many fossils yet. And as we find more and more, it's going to fill in. So we've just hit the gold mine right here in this age, and it will fill out later. And they've found a ton of fossils, but guess what? They're all like here and beyond. So it's just one of those insurmountable hurdles that there is no explanation for it. So what they've tried to do is come up with ideas like, well, maybe it's punctuated equilibrium. You know, they come up with these complex terms like, what is that? So basically, they say, well, maybe, you know, some small organism got isolated somewhere over where we don't see it. There's no